Here are your notes on section 7.3. So we're looking at position, velocity, acceleration, and time relationships. This is really the section that's mostly like doing calculations and stuff, where the last couple things is more just kind of getting an idea of what's happening. Okay, so acceleration of a mass spring system. Okay, the acceleration is not constant. It depends on the position of the object. Okay, so we're looking at the F net is equal to the force, the restoring force, basically. So as this moves, the restoring force will be equal and opposite of our F net, like the acceleration. So restoring force is the negative kx, okay, which is equal to the mass times acceleration, which is equal to F net. Okay, and so acceleration is equal to negative kx over the mass. Remember to have our mass in kilograms. Okay, our x is our displacement in meters. Whoops. And then our acceleration is instantaneous at that point, okay, and it's in meters per second squared, or in newtons per kilogram. Okay, and then our k is in newtons per meter, I believe. Yeah. Okay, the relationship between acceleration and velocity of a mass spring system. So this is what happens. So like as it's at point A, it'll have zero velocity. The velocity increases till it's at our equilibrium, then slowly decreases until it's at our maximum displacement in the other direction. Okay, the acceleration displacement is always opposite. Okay, so as our displacement goes in the negative, okay, our acceleration's in the positive. So our acceleration would be, well, in this case, it would be decelerating in the negative direction, and two negatives equals a positive. Okay, so the force or the acceleration is always back towards the equilibrium, so that's why we get that negative in there, because the force is always towards the equilibrium. Okay, again, the same relationship between displacement, velocity, and acceleration exists for vertical mass spring systems. And so our change in displacement is kind of equal, like our maximum change, we'd have our maximum or zero velocity, maximum acceleration. And then as the acceleration, as it slows down, kind of going towards, okay, then because at equilibrium there is zero acceleration, but your velocity is maximum. Then it'll continue to decelerate until you get, again, zero velocity. Okay, acceleration displacement is always opposite. We already did that one. Okay, maximum speed of a mass spring system. Okay, so again, our energy of like tension is equal to our potential energy max. Okay, which is equal to when the string is stretched as far, or spring, not string, is stretched as far as it'll go. So our displacement max, okay, is equal to 1/2 times our equilibrium constant times our amplitude, or just our maximum x. And so this could be like on your formula sheet, it's EP equals 1/2 kx squared. And then at equilibrium, okay, all of that potential energy, as it's swinging back, becomes kinetic energy. So our ET equals our EK max, which is equal to 1/2 mv squared. At any time in between, you're going to have your mechanical energy, your EM, will equal your EK plus your EP. So like if you're at X over here, and it's not at the max, you can find your EP, and then if you know the speed, then you can find your EK, and you add those two together to find your EM. So yeah, we consider the spring to be frictionless, so the total energy, so in this case, instead of EM, they're just saying total energy, okay, is equal to your potential energy plus your kinetic. Okay, all of the potential energy at the maximum displacement is converted to all the kinetic energy at equilibrium. So with that, our EK max equals our EP max. So if we know our maximum amplitude or maximum x value, okay, then we can find our maximum v value as it swings back towards equilibrium. Okay, this is the formula we can use to find that. Okay, it's just rearranging these two formulas, so you get, okay, amplitude, or x, times the square root of k over m. Okay, and so again, remember that a and x are the same, just a is the maximum x. Okay, and so yeah, maximum displacement. Okay, these examples are out of your textbook. You can read over them if they're, and hopefully they'll help you as you're going through your problems. Okay, another calculation excuse me, we can make is t equals 2 pi times the square root of m over k. So t is our period in seconds, 2 pi, that's just numbers. Okay, m is our mass in kilograms, and then k is our spring constant, okay, in newtons over meters. Okay, so displacement of the mass has no effect on the period, so it doesn't matter how far the mass is going. As long as we know the mass and the spring constant, we kind of know how far or how long it'll take for one period. So again, the period of any simple harmonic oscillator is independent of the displacement from the equilibrium. Okay, and another thing is our period is time it takes for one oscillation. So it has to go like there and back. That is our period. Okay, another example of your textbook. Okay, for a pendulum, okay, and they work this out in your textbook and kind of show you how they get to this formula. Okay, but the period of a pendulum is equal to 2 pi times the square root of L. This is the length of the string of our pendulum times G, or divided by G, which is our gravitational field strength. So the period of a pendulum only depends on its length, not the mass or the bob on the amplitude of oscillation. Okay, so how far you kind of pull it back. So the period, as long as we know the length of the string or the length of our pendulum, this is a constant G as long as we're on Earth, 9.81. So then you can find your period for this. Okay, one thing to note is like mass doesn't matter, because again, like if something's falling, the mass is the same no matter what, or like the acceleration's still the same, doesn't matter on the mass. Okay, if we take out wind resistance and so on. Okay, a pendulum can be used to measure variations on Earth's gravitational fields. So by rearranging this formula, we can come up with this formula. Okay, so we first off, we square everything to get rid of the square root. So we get 2 squared times pi squared times t squared. And because these are under, they stay as L and G. And so that's what we see here. And then we just rearrange. G's on the bottom, T's over here. So we just kind of cross multiply and we get this over here. Okay, another example of your textbook. Okay, those are always good to look at. Don't worry about the snap pages. Okay, you're reading over these pages, or like you don't have to read over them, but that's like you'll have those pages open as you're working through your problems. And like in your workbook, there's a lot of questions that are straight out of the textbook, like what is this definition? So they're all in these pages here.